Okay, we spent a lot of time talking about nuclear fusion because it's such an important thing in astronomy, the source of all the light we see from stars. I'd like to say just a little bit more about nuclear fission, right? That's the other process that can create energy by nuclear reactions. If you remember that there was that binding energy curve, right? As a function of mass, it went up and then it went down again. And the way to generate energy was usually fusion, right? To take light nuclei and put them together into heavy nuclei. But you can also get energy by going up the binding energy curve when you're on the very heavy side. You have really heavy things like uranium and you break them apart. That also gives rise to energy, exothermic reactions, if you recall. Um, so you can get energy by breaking big nuclei apart, as long as the final products have higher binding energies than the initial state, and that does sometimes happen naturally in nature. But of course, one of the aspect of it that we learn the most about often is artificial nuclear reactors, human-made nuclear reactors, and nuclear bombs, of course. Um, the reactions, they are usually of the type listed here, where you have some sort of source of free neutrons that are sort of shot like bullets at these large uranium atoms. Um, Sometimes there can be a neutron capture into a slightly more massive nucleus, but it's an unstable nucleus. And the unstable nucleus wibbles and wobbles around and eventually breaks apart into these products. Um, and interestingly enough, two products of equal masses usually aren't what you get. Usually it's something like this, 60%, 40% distribution in mass. You get energy out of it because the products have higher binding energy by going up the binding energy curve. And you also get these extra free neutrons flying out. And those extra free neutrons are what can actually go on to create the so-called chain reaction. If they go off and hit other nuclei, they'll undergo the same thing, generating more free neutrons and more and more and more. And that's why nuclear reactions can be such powerful things. Now, it's not just the artificial ones. There was this one site in Gabon, West Africa, where it's a deep uranium deposit. And when they looked very carefully at the different isotopes and elements that were present, they realized that about 2 billion years ago, there must have been a long occurring, naturally occurring sort of chain reaction going on there just due to the pressure under the ground. So these things can happen naturally. Um, but normally the things in astronomy and astrophysics that we study aren't these induced reactions, but it's more the natural radioactive decay. Um, because again, these species of these heavy things like uranium are naturally unstable, and they'll naturally break up into smaller things, um, uh, even without being shot by free neutrons. You just have to wait a little longer. So, for example, the big example that we have access to is the interior of the Earth. The interior of the Earth is actually hot. It's heated, and some of the generation of the energy is from these exothermic type reactions that are due to radioactive decay. There are all these heavy elements in the Earth, and if they're radioactive, they'll decay and eventually generate energy. So the amount of power, this is a plot of how much power we believe has been released over time. Today, about 20 terawatts of power is being released. 20 trillion watts is being generated by the Earth. Back when the Earth was first born, it was more like 100 trillion watts, and it's decreased over time because these radioactive species are gradually going away. Right? As they decay, they turn into more stable species. Uranium and thorium eventually turn into lead after many, many different reactions, and they go away. It is kind of interesting that there's this other source of beta decays due to potassium. This is an isotope of potassium that's not the main one, potassium 40, that can undergo either a regular beta decay or an inverse beta decay. Either it's a neutron turning into a proton or a proton turning into a neutron, and it gives off, neutrinos and either electrons or anti-electrons. It's kind of interesting. These anti-electrons or positrons are generated by pretty much all sources of potassium. And, what's one of the big sources of potassium? The good old banana, right? And people have actually figured out, gee, how much antimatter, positrons, does the average banana produce? Well, they worked it out. Only some of it is potassium 40, but the average banana produces one particle of antimatter, one positron, roughly every 75 minutes. That probably doesn't get too far before being annihilated and turned into other energy, but there's an interesting fact about potassium and one of our most common sources of it. But yeah, there's a lot of it in the interior of the Earth. It was actually at the beginning, it was the most dominant, this potassium was the most dominant source of heat, but now it's not. It's because most of it's gone away. We measure these things by measuring neutrinos from all these different beta decays that happen at different parts of the chain from these reactions. It is important to put this 20 terawatts into context, of course, as we're sitting here on the surface of the Earth. If you take all of the solar radiation that's absorbed by the Earth and you work it out, that's actually much, much bigger than all this, right? It's 100,000 terawatts, 100,000 trillion joules per second coming in from the sun. But again, that's only the surface layers, right? If you go down about 100 meters underground, the thermal conditions that you're going to feel have nothing to do with the sun, nothing to do with the seasons even. And it's really all coming from this radioactive heating. We also think this might have happened on Mercury. Mercury is very close to the sun. It's got a large metallic core that's filled with iron and other heavy metals, and we think it's molten. And the reason that it became molten wasn't just the solar input of energy because it's so close, but also a lot of these different radioactive decays that can eventually produce energy. So that's one of the planetary science applications. How do planets retain their heat? We've been looking at these things, and we've been looking at this exponential decay in these heating rates, and it's worthwhile going through the math a little bit more of those. If you remember, we talked about fusion reactions, right? We talked about this reaction rate, and that depended on the product of the N1 and the N2, right? Because we had two different species, plowing into each other and creating a new product. And if you double the amount of species 1 or double the amount of species 2, you'll get double the amount of reactions. That's what the rate measures. So that's nice. Here we're actually in a simpler case because it's a single species that's breaking up into multiple ones. So the rate only depends on how many of the single parent ingredient are there at the beginning. And we can write these rate equations like we did, right? The time rate of change of the concentration, the number density of that species. Well, if it's going down with time, the rate is going to be a negative number minus some rate. And that rate itself has to depend on N1. So it's N1 times a constant. And rather than writing N1 times C, that constant is often written as 1 over a characteristic time, just because, well, look at the units. The units of this equation are N over time. So you might as well write the constant as a 1 over time. This tau constant is a unique property of each kind of radioactive isotope, each kind of radioactive nucleus. There are ways of calculating it, but normally it's just something that we look up. But if we know that number, we can solve the equation, right? We can rearrange it to a dn over n and a minus dt over tau. And what do you do with this? Now that we've separated it, we integrate both sides. The left side will be a log of n1, the right side will be a minus t over tau, and then we solve it for n itself. So n as a function of time is what it was initially, times a function that goes down with time, e to the minus t over tau. And that's this blue thing that's plotted there. So it's dropping exponentially. Oh, and of course, if the number density of radioactive nuclei is dropping exponentially, then the rate is also dropping exponentially, right? Again, the rate is proportional to N1. And then also the energy generation rate that we defined for stars is also the relevant thing for the planetary heating rate, for example. That's going to be how many joules of energy per time are being produced per kilogram of stuff in the core of the Earth. And that's also going to be dropping with time. So that explains the exponential decay on those earlier pictures. Now, we often use this term half-life to talk about the rate of radioactive decay. The half-life is related to this tau, because let's just remember what the tau is. The tau is the number in this denominator here, and when the time goes, 1 tau, right? When you go up, when t equals tau, when you've gone from your initial state to this point where you're now at t equals tau, well, the exponent is minus t over tau. So this is going to be the initial state times e to the minus 1 now. So e to the minus 1, you remember e itself, the constant is 2.7 something. And 1 over e is going to be like 1 over 3 or so. So the tau is what astronomers sometimes call the e folding time of the decay, right? If you wait 1 tau, you'll drop by a factor of e. You'll drop by another factor of e and another factor of e. But again, people don't always think in terms of e. It's maybe easier to think in terms of multiples of 2, right? It'll be cut in half, then cut in half again, then cut in half again. And as you see here, you don't have to wait as long for it to drop by a factor of 2. You just have to wait the so-called half-life. And if you put in half of the initial concentration into that equation and solve for the half-life time, you see that it's 69% or so of tau. So it happens at a shorter time than tau, but it's related to tau. All right, yes. So I guess one of the other applications of this, of course, that is familiar, if you see news about archaeological discoveries, is this concept of carbon dating. And it takes this exponential decay very seriously to figure out how old things are. The carbon that we're talking about here is carbon-14, and it's important to think about where it comes from and where it goes. So we're not just talking about primordial carbon-14 that has been around since the sun was born. In the Earth's atmosphere, the carbon-14 is always continually regenerated because cosmic rays, which are just particles like neutrons, are continually slamming into the Earth's atmosphere and colliding with the molecules of air, for example. Air is mostly nitrogen. And when this happens, you can have a neutron capture reaction where it is absorbed into the nucleus, but then it kicks out one of the protons, and it creates this unstable carbon-14 nucleus. Those carbon-14 nuclei trickle down to the ground, and eventually they undergo beta decay because they're unstable, and one of the neutrons turns back into a proton, and you get back the nitrogen again. And all the products of the beta decay. The half-life of that is something like 5,700 years. Now, of course, this carbon-14 isn't the most common isotope in the atmosphere, right? The most common one is regular carbon-12. The ratio of carbon-14 to carbon-12 is tiny, 10 to the minus 12. So for every trillion regular carbon atoms, there's going to be 1 carbon-14. This ratio, we can give it a name. So when this stuff trickles down to the ground from the atmosphere, all the living plants and animals that are breathing and absorbing carbon from food have the carbon in their bodies with this same atmospheric ratio. But then after time goes by, living plants, animals eventually are buried under different layers of the ground, and they're no longer exposed to this fresh supply of carbon-14 from the atmosphere. All that's left is that the carbon-14 will decay, and its concentration will drop over time. So if you dig up something, or say if you go into a cave here, the Lascaux cave paintings in France, you can look at the charcoal that was deposited onto the walls and measure its component of carbon-14, right? If it was charcoal from torches when these things were first made, yeah, this tells you about how long ago, because you're going to measure a lower concentration. The Lascaux cave paintings have something like 10 to the minus 14, not 10 to the minus 12. And that said that this carbon was last exposed to the atmosphere a long time ago. And you can work it out from the exponential curve that it's something like 19,000 years old. Yeah, I picked this picture. There's a lot of nicer pictures of these paintings. But I picked this one because I didn't even realize how huge some of the paintings were compared to people. Anyway, I think that is it for nuclear fission and radioactive decay. And the last video will just be a summary of sort of some grander themes and where the course is going as a whole.